13.8 billion years ago, the universe won a lottery. Not just once, but dozens of times in the very first moment of its existence. The rules that govern reality, from the strength of gravity to the mass of a quark, were set with an almost unimaginable precision, a perfect balance on the knife's edge of existence. If any constant in this cosmic formula were off by even the slightest fraction, our universe would be a desolate place, filled with black holes, or just a tenuous fog of hydrogen, with no stars, no planets, and certainly no us. This isn't a coincidence. This is a statistical impossibility. While mainstream science attributes this to cosmic luck or the existence of countless multiverses, a sense of unease remains. Is this perfect fine-tuning the greatest fluke of all time? Or is it evidence of something deeper, a law, an intention, or a structure that we are only just beginning to perceive? Tonight, we won't just recount the story of the universe. We will investigate why this story can be told at all. Join me as we explore the greatest mystery of all time. Why does the universe seem tailor-made for us? Part 1. The Planck Epoch. 1/10,000,000,000 of a trillionth of a trillionth of the first second. Where is the hottest place in the universe? You might think it's in the natural thermonuclear reactor at the center of a star. But even if you were incinerated in the plunge through its fiery layers, your journey would be in vain. The temperature at the core reaches a mere 15 million degrees Celsius. You could seek out even more violent phenomena in the cosmos, like supernova explosions. Here, in the spectacular death of a star, superheated shells of gas are blasted out for light years, leaving a gravitationally crushed neutron star at the center. The temperature here far exceeds ordinary stellar furnaces, reaching 100 billion degrees Celsius, but this is still not the hottest. In fact, the highest temperature ever recorded anywhere in our vast universe was beneath 100 meters of snow cover near the shores of Lake Geneva, in Switzerland. And it didn't come from a natural process but from the coordinated effort of hundreds of scientists and billions of euros in research and development. In CERN's Large Hadron Collider, where individual particles are regularly smashed together at near light speed, the collision of two lead atoms in 2012 generated a fleeting temperature of around 5.5 trillion degrees Celsius, 50 times hotter than a supernova. But even this number is nothing compared to the highest possible temperature. Temperature is simply a manifestation of a particle's energy, its motion, or how fast it vibrates. Absolute zero, equivalent to minus 273.15 degrees Celsius, is the lowest limit where particles would theoretically stop moving altogether. But there is also an upper limit, an absolute hot, that marks the highest temperature before particles themselves are torn apart by their own energy. It is called the Planck temperature, and it's around 1.4 times 10 to the power of 32 Kelvin. Max Planck, who gave his name to this unimaginably searing temperature, was a dedicated German theoretical physicist who found his academic stride at the turn of the 20th century. His ideas are considered foundational to quantum physics and led to the quantization of light into discrete packets of energy called photons. But they also led him to consider the fundamental quanta of other natural phenomena. Using universal quantities like the speed of light and the gravitational force combined with the eponymous Planck constant he derived from his work on electromagnetic radiation, he defined the Planck length, the smallest quantum of distance, at around 1.6 times 10 to the minus 35 meters, about 100 quintillion times smaller than a proton. The time it takes for light to travel this infinitesimal distance in a vacuum is the Planck time, coming in at 5.39 times 10 to the minus 44 seconds. And the Planck temperature, the effective measure of absolute hot, is the temperature at which the wavelength of thermal radiation reaches the Planck diameter. It can get no smaller. These numbers are beyond our true comprehension. We are evolved to be familiar with scales relevant to us. And so, it might seem that these Planck units are too small or, in the case of temperature, too large to be of any practical use. But it is in contemplating the infinitesimal moment at the very beginning of our impossibly vast universe that these units truly come into their own. Because our universe is expanding, becoming less dense, and has been for its entire history. Scientists don't know if our universe is infinite, but if it is, it always has been. So, rather than starting from a single point, it would also have started infinitely large, and rather than growing over time, it would simply be getting less dense. Our observable universe, however, is different. It is the only part of the universe we can see or interact with, and is limited by the speed of light and the distance it has been able to travel since the universe's birth 13.8 billion years ago. But as we wind back the clock, that observable part of the universe shrinks and becomes more condensed, until eventually we reach a time when everything inside it was just 1 unit of Planck time old, 1 Planck length in diameter. And with our entire observable universe compressed into such a tiny space, the temperature of the entire universe sat at precisely the Planck temperature. This moment, 100 millionth of a trillionth of a trillionth of a trillionth of a second after the beginning of time and space, is known as the Planck Epoch. And it was a very strange time. In today's universe, everything we experience is governed by immutable laws of nature, ultimately controlled by the interplay of 4 fundamental forces: the strong force that holds atoms together, the weak force that governs certain types of radiation, the electromagnetic force that distributes energy over vast distances, and gravity. As Max Planck had predicted at the end of the 19th century, the strong, weak, and electromagnetic forces can be quantized, represented, and treated as tiny and indivisible packets of interaction, just like particles of matter. These messenger particles are known as gluons, W and Z bosons, and photons respectively. But gravity is different. With his theory of general relativity, Albert Einstein overturned the classical mechanical definition of gravity. Instead, he conceptualized it as the curvature of spacetime, a warping in the very fabric of reality. Through various large-scale experiments, general relativity has been verified time and time again, and the curvature of spacetime caused by gravity is now recognized as an inherent property of the universe, affecting all matter and energy within it. Consequently, in the Planck Epoch, long before any of the conventional laws of nature took hold, it was gravity itself that manifested first. But there's a problem. Everything we know about how gravity works today is based on Einstein's successful theory, but that theory has only really been tested and verified on larger scales. In the Planck Epoch, however, our entire observable universe was compressed into an area trillions of times smaller than a proton, and general relativity simply doesn't help. Instead, the dynamics of the very small are governed by quantum mechanics. At scales small enough for us to consider individual subatomic particles of matter, or the quantized messenger particles of force and energy, a completely different set of rules takes hold, where nothing is where you expect it to be and the very act of observation changes the outcome. Instead of dealing with absolute values, quantum physicists look at probabilities, and nothing stays the same for long. Luckily for us, this lawless quantum world only reigns supreme on nanoscopic scales, and by the time we get to magnitudes we are more familiar with, the probabilistic weirdness averages out. But in the universally nanoscopic Planck Epoch, there was no escaping the quantum. And this is the problem with understanding how everything really worked in that moment. General relativity and quantum mechanics are fundamentally incompatible. So, researchers are still searching for a solution, something called quantum gravity, that can reconcile 2 of the most important theories in modern physics, and properly describe how the Planck Epoch universe behaved. Unfortunately, it's a question that cannot be reasonably solved by experimental means. Considering the massive energies required to create and study the other force messenger particles inside collider facilities, and the higher plane that gravity occupies in defining the entirety of spacetime, it would take a particle accelerator almost the diameter of our entire solar system to generate enough energy to truly probe gravity in the extreme conditions of the Planck Epoch. But this hasn't stopped theoretical speculation and extrapolation. One idea suggests that, like the other fundamental forces of nature, gravity is also transmitted by a messenger particle, a quantum unit of gravitation that has come to be known as the graviton. But gravity is so much weaker than the other forces that its meager messenger particle is practically undetectable. Another theory, known as loop quantum gravity, is very different. In it, physicists envision the smooth and ever-changing geometry of spacetime is ultimately pixelated at the smallest scales, and by rewriting Einstein's general relativity equations in terms of lines or loops instead of points, the calculations for gravity at the quantum scale become far more manageable. And perhaps the leading candidate for a viable quantum gravity solution continues to simmer in the background of theoretical physics. String theory envisions the point-like particles of traditional physics as one-dimensional vibrating strings, and it is the vibrational state of the strings that determines what a particle is, as well as the elusive force of gravity. To make the mathematics of string theory work, however, no fewer than 10 or 11 dimensions are required, many of which are folded up inside the strings themselves, or are partitioned into 2- or 5-dimensional structures known as branes, the fundamental objects of an even more elusive overarching theory with the simple name of M. Each hypothesis for how quantum gravity might actually work is more mind-bending than the last, rooted in the abstractions of mathematics, all but impossible to visualize. And yet, that is exactly what we are trying to do as we wind back the clock to picture the very first moment of our universe in the Planck Epoch. Ironically, it was back in the 1950s, when the science of quantum mechanics was still in its infancy, that American theoretical physicist John Archibald Wheeler gave us a tangible description of the conditions during that chaotic and incomprehensible period. He envisioned the early universe as consisting of a seething and dynamic quantum foam. This quantum foam, as Wheeler described it, arises from the dynamic and unpredictable nature of interactions at the quantum scale. Heisenberg's uncertainty principle severely curtails the ability to define length, time, or energy at any given point in a Planck-sized universe, and so, the continuous and tightly woven spacetime we are familiar with today is replaced with a foam-like texture that is inherently unpredictable and randomly fluctuating. Microscopic quantum black holes and wormholes spontaneously pop in and out of existence without clear cause and effect. In this miniature, hypercondensed, and energetic universe, for the briefest of moments, anything was possible. But after just 100 millionth of a trillionth of a trillionth of a trillionth of a second, the pervasive unpredictability of the Planck Epoch came to an end, as the gradual and infinitesimal expansion and cooling of the universe signaled a new era. The universe would not look or behave anything like it does today for some time, but from here on out, our current theories at least have a chance of describing what was going on. Part 2: Grand Unification, 1 trillionth of a trillionth of a trillionth of the first second. Everything in our universe is controlled and defined by the 4 fundamental forces of nature. Imagine you turn on the television. Gravity keeps you firmly in your seat, holds the Earth's atmosphere close to the surface, and keeps the Earth orbiting our nearest star, creating a habitable environment for your existence. And yet, for all that, gravity is comparatively weak, and you can overcome it with just the muscle of one arm to pick up the remote control. In response to your button press, invisible infrared light, electromagnetic radiation, beams across the living room from the front of the control. The image comes to life before you, through millions of tiny pixels emitting visible light, another form of electromagnetic radiation, traveling back across the room and into your eyes. Your eyeballs themselves are marvels of evolution, but ultimately they depend on the properties and behaviors of the atoms inside, the electrons and nuclei held together by the electromagnetic force. The atomic nuclei themselves are held together by the strong nuclear force, protons and neutrons squeezed together at the atomic center. Not only that, but these protons and neutrons are actually combinations of 3 smaller subatomic particles, called quarks, also bound by the same attractive force. Every atom in your body, in the television, in existence itself, depends on this force. As your eyes focus and you engage with the moving pictures on the screen before you, each nerve in your brain fires up to 200 times a second. All of that coordinated electrical potential depends on the proper potassium balance in your body. Like other elements, potassium is held together by the strong nuclear force, but there is something else at play as well. For potassium is very slightly radioactive, and around 5,000 atoms of potassium undergo radioactive decay every second, a decay driven by the weak nuclear force. And 150 million kilometers away, the core of our sun burns with the heat of a stellar furnace, powered by the fusion of hydrogen into helium. This incredibly powerful reaction is responsible for the heat that keeps the Earth habitable, and on a galactic scale, for the very elements that make up the planet, the television, and you. And all of this also depends on the weak nuclear force. It may be weak by name, but its power is immense. Each of these 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, together shape our experience of the universe. And that has been true for the vast majority of our universe's billions of years' history. But in the very first moments of time, the conditions created a very different set of rules, derived from the same fundamental physical ingredients. In the Grand Unification Epoch, which followed the Planck Epoch, there were only 2 forces. But how could this be? The key to visualizing this lies in the flipping of a coin. Flip a coin to decide between 2 equally weighted options. Heads for one team, tails for the other. The decision is only made when the coin comes to rest after the flip, when the energy supplied by the flexing of thumb and forefinger has been exhausted, and the metal disc comes to a halt. Before that moment, when the coin is still imbued with energy, and it is spinning in the air or on the table, it's all but impossible to distinguish its two faces, the two options available to you. There is just a single spinning orb with its own unique characteristics. This is what we are faced with when we consider the behavior of the fundamental forces at higher energies, the energies that existed in the early universe. Crank up the temperature significantly, and the individual properties of the weak nuclear force and the electromagnetic force begin to wane and blend together. We no longer see the separate heads of electromagnetism and tails of the weak force, but the spinning, faceless coin of two unified forces, the so-called electroweak force. Crank that energy up even higher, and the spinning coin concept applies again to the strong force and the electroweak force. With a high enough temperature, they too blend into a single unified whole, in a process known as grand unification. This ultimate unification of three of the main fundamental forces gives rise to what is known as the electronuclear force, though this neat spinning coin theory of grand unification is yet to be definitively proven experimentally. Even if high-energy collisions inside particle accelerators can show us the combination of the electromagnetic and weak forces, it would take around a million times more energy for the strong force to lose its identity in the same way. Even the highest energy phenomena in today's universe, like supernovae and the jets emanating from the poles of black holes, are still a million times too weak. And as for whether gravity, the fourth fundamental force, was ever accepted into the unified fold, that is a question for the mysterious and unpredictable Planck Epoch, and another problem for the competing theories of quantum gravity to solve. And yet, grand unification theory, as it is known, is a strong candidate for explaining the workings of the universe immediately after the Planck Epoch. Over a period around 10 million times longer than the entire Planck Epoch, the universe expanded and cooled. But it's a testament to just how small things started that, even at the end of this period, the entire universe was still smaller than a single quark, the smallest known particle of matter today. With the latent energy of that universe compressed into such a tiny space, temperatures reached 100,000 trillion Kelvin, around 1 trillion times higher than the Large Hadron Collider has ever achieved. These were the conditions for the grand unification epoch, ruled by the strange electronuclear force and the bizarre interactions it brought with it. The infinitesimal universe was filled with particles undergoing an extreme identity crisis. Photons spontaneously transformed into matter-antimatter pairs, creating quarks and leptons. But these fledgling particles were extremely short-lived, decaying quickly back into photons as soon as they were formed. The electronuclear messenger bosons only complicated the picture, helping quarks to turn into leptons, leptons into quarks, matter into antimatter, and back again. Under the chaotic rule of grand unification, it was a free-for-all of energy and matter, of virtual and real particles. Until 1/1,000,000,000 of a trillionth of a trillionth of a second after the beginning, the coin dropped. The temperature fell to just 1,000 trillion degrees, cool enough for the strong force to break away, for two forces to become three, and for everything to change once again. However, there's a problem with this picture. While these theories may adequately describe the behavior of particles in the first moments after the Big Bang, they fall short in explaining the large-scale universe that would come later. When comparing the initial conditions to the final outcome of the universe, the Big Bang seems to have been bugged. Somehow, this separation of forces played out perfectly to create a universe that was not only viable but structured, stable, and ultimately, alive. This was the first crack in the armor of randomness. Part 3, Inflation, 1/1000,000th of the first second. In July of 2022, the iconic James Webb Space Telescope was firmly established in its orbit around the Sun, 1.5 million kilometers away. After a nail-biting month-long journey and a nearly year-long period of deployment and calibration, it was finally ready to begin its scientific operations. But as it trained its 18 gold-plated mirrors on some of the deepest reaches of the observable universe, scientists were shocked. After seeing the images returned from the revolutionary telescope, American astrophysicist Alison Kirkpatrick wrote in the scientific journal Nature that she found herself awake at 3 in the morning, wondering if everything she had ever done was wrong. Within a month, These images and Kirkpatrick's comments had taken on a life of their own. The constant speed of light means that the deeper we look into space, the further we look into the past. And at distances corresponding to just 200 million years after the beginning of everything, the James Webb Telescope saw galaxies. Not only that, but these galaxies were arranged with far more orderly structure than anyone thought possible. Theories of star and galaxy formation had no way of explaining it, and it was this that had Kirkpatrick worried. Unfortunately, it wasn't long before her concerns were extrapolated to cast doubt on the Big Bang itself, with some media outlets claiming that the next-generation telescope had disproven the landmark theory with its very first images. Thankfully, those concerns were misplaced. Kirkpatrick was only concerned about existing theories of galaxy formation, not the creation of the entire universe. The inexplicable structure of early galaxies meant there was a missing piece in our understanding, not that everything we knew was wrong. And so the Big Bang is safe for now at least. But as a complete explanation of how our modern universe came to be, it has been under much more serious threat for a long time. When we look at the large-scale structure of the universe today, there are several phenomena that don't quite add up. First is the average temperature. Although stars burn at several million degrees Celsius and empty space shivers at just a few degrees above absolute zero, the average temperature we observe in one direction is remarkably similar to any other direction. 2.7 Kelvin everywhere in the universe. All 93 billion light-years of it. But how? If the universe has been gradually expanding for almost 14 billion years, how could 2 points more than 14 billion light-years apart have averaged out without breaking the speed of light? The fact that we see such thermal uniformity now implies that there was thermal uniformity from the very first moments of the universe, a fact that seems extremely unlikely given the nature of quantum fluctuations in the tightly packed early universe. This is known as the uniformity or horizon problem. But there's more. Einstein's theory of general relativity describes how massive objects create curves in spacetime, which then governs the movement and evolution of matter within that spacetime. Stars, galaxies, and black holes leave dents and divots in the local scale structure of spacetime, but when we zoom out to a larger scale, those imperfections are smoothed out to leave a smoother structure that, like the average temperature of the universe, appears to very, very little. The universe, on the largest scales, appears to be flat. If the overall density of matter in the universe was great enough, spacetime would be referred to as positively curved, bending back on itself like the surface of a sphere. This would mean that eventually, the gravity generated by all the matter in the universe would be sufficient to slow and eventually reverse the trend of expansion, collapsing the universe back in on itself in a so-called big crunch. Conversely, if the overall density was much lower, it would result in a negative curvature of spacetime, bending outwards in an open fashion like the surface of a saddle. With this geometry, gravity would never overcome expansion, and the universe would continue to grow forever. Which of these overall geometries is true has massive implications for the future evolution of our universe, and so, trying to measure the overall curvature of the universe we can see has been a preoccupation of astronomers. And counterintuitively, it appears to be perfectly flat. Like the horizon problem, the chances of this being the case are infinitesimally small, equivalent to flipping a coin and having it land perfectly on its edge. For obvious reasons, this has become known as the flatness problem. These aren't just academic puzzles. They are clues that our understanding is incomplete. A random universe should be neither uniform nor flat. The existence of these features suggests a powerful, non-random mechanism was at play in the very first moments, one that tuned the cosmos. On a December night in 1979, theoretical physicist Alan Guth came up with a startling solution. Rather than a gradual expansion, Guth found a mechanism by which the universe could have inflated suddenly and almost instantly to many times its original size, before slowing down and continuing a more linear expansion. The inflationary period Guth proposed would have seen the universe double in size around 90 times in less than a trillionth of a second, resulting in an exponential expansion that would fundamentally change the face of the universe. This incredible inflation is what Alan Guth proposed for the entire universe. In less than a trillionth of a second, the hot, superdense universe exploded to over an octillion times its original size. This, if anything, is what put the bang in the Big Bang. The universe, which a moment before seemed so hot, energetic, and full, was now vast, empty, and cold. It seems drastic, but was actually an elegant solution to the problems plaguing the Big Bang theory. The thermal uniformity problem is only a problem if the uniformity we see applies to the whole universe. But inflation allowed for the compact early universe to contain extreme thermal variations, which were then flung far apart during the exponential expansion. Our observable patch of the universe simply represents a tiny portion of the whole, which was in thermal equilibrium with itself before inflation happened. Similarly, the flatness problem of spacetime curvature is only a puzzling coincidence if the flatness we see applies to the whole universe. But if we are only seeing a small patch of the whole, there's no telling if this is the case or not. Could be a matter of perspective. Inflation has now become a firm part of our understanding of the universe's first moments. The timing of this dramatic period coincided with the drop in energy and cooling that saw the end of the grand unification of the fundamental forces and the emergence of the strong nuclear force. It is theorized that the decay of the X boson messenger particles created a powerful inflationary field, carried by a new messenger particle called the inflaton. This new, overwhelming inflationary energy drove the exponential expansion of the universe, which saw quantum-scale irregularities replicated instantly into large-scale structure. Fleeting quantum fluctuations became overdense and underdense regions of matter and energy, providing the seeds for galaxy clusters and superclusters in the modern universe. All this expansion inevitably cooled and emptied the universe, resulting in a 100,000-fold drop in the average energy levels. Scientists are still not sure exactly why inflation stopped, but when it did, the inflaton field and particle decayed away, dumping much of that energy back into the universe in a period known as reheating. It was this that allowed for the decisive creation of matter, and now, in a larger and more spacious universe, the laws of nature were approaching something we could finally understand and model. This was the electroweak era, which lasted until around 1/1,000,000th of a second after the Big Bang. There were quarks and leptons, matter and antimatter, all governed by gravity, the strong nuclear force, and the strange electroweak force. But temperatures and energies were still too high for the strong force to have any real effect on the supercharged particles in this post-inflationary storm. Similarly, the electroweak force had little effect on matter-energy interactions. And while gravity may have imbued the universe since the beginning, there was still a key ingredient missing, which rendered it almost powerless. Until the newly formed particles were endowed with mass, they remained unruly and untethered. It would take another energy drop and another cosmic transformation before we would get to a universe we would begin to recognize as our own. You bet. We're now moving into the core of the fine-tuning mystery, where mass and asymmetry emerge to sculpt the universe as we know it. Part 4, Higgs and mass, 1/1000th of the first second. Symmetry is everywhere. Wherever we look in nature, we find balance, regularity, and geometric harmony, whether in our own bodies or the bodies of all animals, great and small. We are bilaterally symmetric, mirrored down the middle, and perceive the greatest beauty in those with the most perfect symmetry. And in science, symmetry has a much broader meaning. It means something doesn't change. From the laws of physics to the conservation of energy and momentum, the universe is inherently symmetric. Positive charges are balanced with negative charges. Some particles spin clockwise, others counterclockwise. And yet, the universe is not perfectly symmetrical. Just as the human body, on closer inspection, has a heart that's off to one side, so too are there imperfections in the universe's perfect balance. There is an imbalance in the amount of matter and antimatter. There are things an electric field can do that a magnetic field can't, even though the two are theoretically equivalent. And many of these imbalances are key to the workings of reality. But it didn't start this way. Indeed, for around the first trillionth of a second, cosmologists believe everything was perfectly symmetrical. There was balance. But that all changed with the final separation of the forces and the emergence of something that would affect the vast majority of existence, mass. Just as a drop in temperature signals a phase change in water, from steam to liquid to solid ice, fundamentally altering its properties at each transition and reducing its symmetry, so too did a drop in temperature in the young universe bring about phase changes in the energy and matter that filled it. As the four fundamental forces finally fully separated and crystallized into distinct entities, we see the dawning of a new era, the Planck Epoch, defined for the first time by the interaction of matter. The single largest object detected in our universe is probably the hypergiant star UY Scuti. With a diameter around 1,700 times greater than our own Sun, if it was at the center of our solar system, its outer edge would sit just beyond the orbit of Jupiter. And yet, this star, like all others, is almost entirely composed of some of the smallest things to be found in the universe, individual atoms of the light elements hydrogen and helium. Hydrogen is the smallest of all the atoms, which were themselves once thought to be the smallest possible thing. But we now know, thanks to revolutions in atomic theory throughout the early 20th century, that the atom can be split. Hydrogen and helium, though simple, are composite particles of protons, neutrons, and electrons. But even these are not the smallest fundamental particles. Protons and neutrons themselves are composites of even smaller units, called quarks, whose various properties, along with those of electrons, ultimately govern the characteristics and behaviors of everything. This picture, which has come to be known as the standard model of particle physics, is in theory all we need to explain why everything looks the way it does in the universe today. Normal matter is composed of protons and neutrons, which are made up of combinations of quarks. There are different quark flavors, with whimsical names like strange, charm, top, and bottom. Meanwhile, the electrons that orbit the atomic nucleus appear to be indivisible too. They are a type of particle called a lepton. So, our standard model consists of 12 fundamental, indivisible matter particles, 6 types of quark and 6 types of lepton, along with the antimatter partners of each, and the messenger particles of the fundamental forces. At least, almost everything. There was one important piece missing from our model until recently, and that was mass. Every element in the universe, from hydrogen to plutonium, has its own characteristic mass, which corresponds largely with the number of protons and neutrons in its nucleus. So, the vast majority of the mass of an atom comes from those protons and neutrons. But when we look deeper and smaller for the ultimate origin of that mass, that is not what we see. As it turns out, a proton is significantly heavier than the sum of its parts. The fundamental particles at the center of a proton are 3 quarks, but their mass only accounts for 9% of the proton's total mass. The rest comes from the energy stored inside that nucleus, from the intrinsic relationship between energy and mass that Einstein identified with his famous E=mc² equation, and from the strange quantum interactions of gluons, the intermediary particles of the strong nuclear force. But quarks still have mass, something separate, distinct from this energy. And the reason for this was a mystery for a long time. Photons and gluons do perfectly well without any mass. Electrons and neutrinos have even less than the smallest quarks, while the weak force-carrying W boson is around 40,000 times heavier than an up quark, heavier than an entire iron atom. What causes this incredible mass discrepancy, and why do particles have mass at all? This was the question that troubled British theoretical physicist Peter Higgs in the 1960s. To solve the problem, he proposed that all particles first came into being in the universe with no mass at all, and that at some point in the first fraction of a second, a new kind of energy field emerged and imbued the entirety of spacetime, endowing different particles with the property of mass. This Higgs field, as it came to be known, would be transmitted by its own quantized messenger particle, called the Higgs boson, which would sit alongside the other 16 particles of the standard model. And yet, although Higgs' theory was plausible, it took almost 50 years to finally find the elusive Higgs boson. Finally, in 2012, experiments at the Large Hadron Collider completed this seemingly impossible task. Scientists confirmed they had indeed found the Higgs boson, and in doing so proved the existence and operation of the Higgs field, once and for all. 1/1,000,000,000 of a second after the Big Bang, the electroweak force catastrophically separated in two, ending the perfect symmetry of the universe as the W and B bosons that carried it decayed into the photons of the electromagnetic force, and the W and Z bosons of the weak nuclear force. But this was just the beginning of the symmetry breaking. The emergence of the Higgs field around this time endowed the real and virtual particles, spontaneously created during inflation and the electroweak separation, with mass. W and Z bosons became heavy particles. Quarks and leptons received their masses according to flavor and type, while photons and gluons continued to be massless and untethered by the Higgs as they had been before. As the quark epoch was fully realized at 1/1000,000,000 of a second after the Big Bang, The universe was finally filled with all the ingredients, the characteristic particles and the characteristic forces, needed to make stars, planets, and us. The quark-gluon plasma that imbued the inflated universe was the primordial soup from which all structures in the universe would be made. But the very emergence of the Higgs field begs a profound question. Why did it give particles these specific masses? Why is an up quark heavier than an electron but so much lighter than a W boson? Nothing in the Standard Model can account for these values. They appear to be completely arbitrary. But they are anything but arbitrary. They are fine-tuned. If the masses of the fundamental particles were even slightly different, the universe as we know it could not exist. This is where the staggering coincidence transforms into a disturbing mystery. The universe didn't just happen to exist. It happened to exist in a way that allowed for complexity. And the biggest clue lay in another asymmetry, an imbalance that was baked in at this very moment, one that saved reality from complete annihilation. Part 5. Fine-tuning protons, neutrons, and antimatter 1/1,000,000th of the first second. Our universe is filled with incredible variety and richness. There are stars that burn hot and fast, exploding spectacularly after a mere million years, and others that smolder slowly, unchanging for trillions of years. There are countless planets, gas giants, scorched barren rock worlds, and occasionally, blue, wet worlds ripe for life. In the possibly infinite expanse of the universe, there is almost infinite scope for variety. But there are also certain aspects of reality that are immutable and constant, no matter where you are in the universe or how you observe them. These natural constants have been revealed one by one, as scientists have expanded our understanding of how the universe works, and why it works the way it does. Time and time again, we have stumbled upon seemingly magical numbers that have no relation to any other physical law or phenomenon. Like the speed of light in a vacuum, which is generally considered the absolute speed limit for anything moving in the universe. Or the universal gravitational constant, which describes how strongly two objects will attract each other due to the force of gravity. And the list goes on. There are precise and definable constants that relate the energy of particles to their temperature, or temperature to the amount of radiation emitted. Less obviously, but just as important, the mass of the fundamental particles is also set at constant, yet seemingly arbitrary values, a fact that not even the Higgs mechanism can explain. Why do these natural relationships have these exact values? This was a problem that vexed even the great physicist Richard Feynman as he considered what is known as the fine structure constant, which essentially describes the strength of electromagnetic forces between particles. Its value is a little over 137, but there is no relationship between it and any other law of physics, no reason why it couldn't have been 12 or 135 or 3015. But the fact that it is 137 and not any other number is incredibly important to the overall state of the universe. If it was much larger or smaller, it would drastically affect the stability of protons in the universe, meaning that matter would be unlikely to hold together at all. And the same applies to most of the other natural constants. If gravity were weaker than it is, the universe would be filled with nothing but an ever-thinning soup of hydrogen gas. If it were stronger, all matter would be sucked into black holes or violent, short-lived stars with no room for planets and life to form. Many of the natural constants seem arbitrary, but they are also delicately fine-tuned to allow for the rich and diverse universe we inhabit. But why? We still don't know. Is it just a lucky coincidence? The sign of a guiding creator? Or, as many scientists theorize, is our universe just one of countless others, all created with different initial conditions and different values for these fundamental constants, the vast majority of which have resulted in failed, barren universes, and only those in which the values were just right could foster cosmic diversity, longevity, and, consequently, us. Whatever the reason, this fine-tuning was critically important in the very first moments of existence. By the time 1/1000th of a second had passed since the Big Bang, the universe was filled with an incredible number of quarks, leptons, and virtual particles. But temperatures and energies were still too high for any of these fundamental particles to meaningfully interact with one another. The temperature dropped, and by 1/1,000,000th of a second after the Big Bang, the universe was a mere 1 trillion degrees Celsius. Gluons and quarks finally slowed their frenetic vibrations, allowing them to interact with one another for the first time. Protons and neutrons are composite particles, each made up of 3 quarks. But as it turns out, the internal structure of a proton is even stranger than we could have imagined. Not only is the vast majority of the mass made up of energy and quantum dynamics, but the composition of matter isn't as fixed as we might think. The inner workings of protons and neutrons may be truly bizarre, but in the first millionth of a second of the universe, they were becoming an increasingly prominent part of the fabric of the cosmos. And yet, thanks to the effects of the weak force in this hot, dense plasma, newly formed protons could easily change their identity to become neutrons and vice versa. It was only when the temperature dropped even further, as the universe approached 1 second old, that this particular characteristic of the weak force became less effective and protons and neutrons finally slowed their transformations. In this so-called freeze-out, hadrons picked an identity once and for all. And it was as this happened that the seemingly arbitrary fine-tuned natural constants, in this case the mass of the up and down quarks, got their first real chance to shape the future of our universe. Because down quarks are heavier than their up cousins, and neutrons contain 2 down quarks, the mass of a neutron is slightly greater than a proton containing 2 up quarks. So, as the identity transformations finally played out in an ever-cooling universe, the energy slope from heavy neutron down to lighter proton was favored over the energy-intensive climb in the opposite direction. It was this very small mass difference that ultimately resulted in an imbalance in the number of protons and neutrons in the universe from that point forward, with a ratio of around 7 protons for every neutron. And this, as it turned out, was to be a crucial ratio for the formation of the universe as we know it. If things had started differently, if the down quark was assigned a slightly lower mass during the fine-tuning of our reality, then the universe we see today would be very different. If neutrons were lighter than protons, it would have been them that were favored in the freeze-out. With more uncharged neutrons than protons, there is a limit to what chemistry can reasonably do. We would have been left with a cold, dark universe with no stars, no galaxies, no planets, and certainly no us. We can, therefore, be thankful for the universe's inexplicably pro-proton slant. But this wasn't the only imbalance baked into the cosmos at around this point in its evolution. There was also a mysterious but fortuitous lack of antimatter. One day in the future, as we look up into the skies, we may be looking in just the right direction at just the right time to see an alien civilization unmake itself. In the beginning, antimatter would have been formed in parallel with matter, with particle pairs forming from spontaneous energy transformations in the first billionth of a second of the universe. But in such a dense environment, they would not have lasted long before encountering their partner, mutually annihilating, and turning back into energy. This process of spontaneous creation and destruction continued until the temperature of the universe dropped, and no new quark-antiquark or lepton-antilepton pairs were created. But gluons didn't distinguish what kind of matter they assembled, and as protons and neutrons were first created, they came with an equal number of antiprotons and antineutrons. Everything should have been in balance. At this point there should have been no difference in the number of matter and antimatter, and because the 2 types of particle behave identically, and are also only ever destroyed in pairs, the numbers of each should have continued to be equal. But that's not what we see. At some point, between 1/millionth of a second and 2 minutes in the universe's timeline, the balance between antimatter and matter shifted, until there was only 1 antimatter particle for every billion particles. And to this day, physicists are not sure why. This is the most crucial fine-tuning of all. Without this minuscule imbalance, just 1 matter particle left over for every billion matter-antimatter pairs that destroyed each other, there would be nothing. Just a structureless sea of photons. Our entire observable universe, with its hundreds of billions of galaxies, is built from those leftover particles. Our existence is a statistical rounding error. Scientists speculate there may be an undiscovered particle, perhaps a type of heavy neutrino, that decayed asymmetrically, favoring matter over antimatter. Whatever the mechanism, the result is undeniable. The universe chose matter. It broke perfect symmetry to create something from a virtual nothing. Coincidence? Or a fundamental law of reality we have yet to understand, one that ensures that universes don't just pop into existence, but survive to create structure, complexity, and eventually consciousness. Part 6: Neutrinos and Primordial Black Holes, the first second. When we look into the deepest reaches of the night sky, we are greeted by wonders at almost every wavelength. But these quasars also illuminate another strange feature that imbues deep space, known as the Lyman alpha forest. The constant speed of light through the expanding vacuum of space means that the further away an object is, the older it is. So, when we see quasars at great distances, we are seeing them as they appeared billions of years ago. But as we examine the spectral signatures of such distant and ancient quasars, there is more to see than just the redshifted light they emit. At shorter wavelengths, there are also sharp dips in the light we see, and sometimes so many that they cluster together densely, like a thicket of tall pine trees on a high mountainside. This is the Lyman alpha forest, and it is created not by trees, but by low-density clouds of hydrogen gas that lurk in intergalactic space. That hydrogen went on to become the nursery for stars and galaxies, and was itself seeded in the first moments of the universe's existence. By the time 1 second had passed in the cosmic story, a lot had happened. It was now a mere 10 billion degrees Celsius. It was filled with the victors of the brutal particle battles, along with the energetic photon shrapnel from countless mutually annihilating encounters. Up until now, the workings of the 1 second-old universe have been largely in the realm of theoretical physics. But we are now entering an era of the universe that can be more meaningfully studied by experimental physicists and even astronomers. We are finally approaching a part of cosmic history that we can hope to observe and even map. To do that, we need a different kind of messenger. In the frozen wastes of Antarctica, for a few weeks every year, the sun does not set. And this is when they begin. Blasting hot water directly down into the ice. In January 2005, scientists working at the state-of-the-art IceCube Neutrino Observatory began the arduous 58-hour process of creating the first of the 2.5-kilometer deep boreholes required. The first of 80. Instead of pointing up at the night sky, it looks down and through the Earth. It has no lenses, mirrors, or radio dishes, but is instead made up of over 4,000 modules suspended on over 80 strings deep in the ice holes, hanging like pearls in the cold, dark of the Antarctic depths. This might sound counterintuitive, but it is in fact the ideal kind of structure to observe one of the most elusive particles in the entire universe, the neutrino. 100 trillion of these ghostly particles are passing through our bodies every second, without us having any idea of their existence. But neutrinos carry secrets. Because they rarely interact with anything, they could travel straight through the dense, early universe, a period when even light was trapped. Less than a second after the Big Bang, neutrinos and antineutrinos were just another part of the hot cosmic soup. They collided and scattered. But at around the 1 second mark, the temperature in the universe dropped to 10 billion degrees Celsius, and the respective particles slowed down. Eventually, they were moving slowly enough that neutrinos could break free. They no longer collided with matter or light, and were able to escape to leave their imprint on the universe. And so, if we could find that imprint, known to scientists as the cosmic neutrino background, it would represent a picture of the universe at just 1 second old, extending our astronomical vision back in time by around 380,000 years. But these relic neutrinos are even more elusive than their high-energy counterparts. To detect them directly, we would need to build our instruments to be around 1 billion times more precise than they currently are. And this isn't the only modern mystery that may have its origins in the 1 second old universe. This is TON 618. At around 18.2 billion light-years from us, it burns with a brightness around 140 trillion times that of the Sun. It is thought to be nearly 11 billion years old, and despite its staggering luminosity, it is actually home to one of the largest black holes in the universe. Understood to be a supermassive black hole at the center of a galaxy, TON 618 has a mass of around 66 billion times that of our Sun. These hot, massive hearts are thought to grow by gobbling up stellar material from their galactic retinue. But there's something about the timing of these supermassives that doesn't quite add up. As astronomers survey the skies, they are finding these gargantuan black holes that date to just a few million years after the Big Bang, even though our models don't allow for the birth and death of enough stars to feed such early behemoths. A potential solution to this puzzle can be found in a theory that was developed years before we were even aware of the oversized early supermassives. In 1971, Stephen Hawking proposed that there was another way to form black holes, without any stellar precursor, but instead from density fluctuations in the early universe. He called them primordial black holes. In the radiation-dominated era, when the universe was still an energetic plasma of photons and matter, large inhomogeneities, essentially clumps of matter, would have been the result of the inflation and subsequent reheating of quantum irregularities in the very early universe. The universe's inherent gravity would have acted on these density contrasts, collapsing vast regions of gas in on themselves. However, there was only a window of around 1 second after the Big Bang when this could have happened, before the universe expanded and cooled to a size where gravity was no longer effective at pulling matter together into these black hole prisons. But these primordial black holes could be the seeds for the otherwise inexplicable supermassives we are detecting today. These black holes, created not from the collapse of stars but from the very fabric of early spacetime, could be the missing pieces in the story of cosmic structure. They could be the explanation for dark matter, the seeds that gathered the first galaxies. They represent another path, another way to create complexity from the initial chaos. One that doesn't depend on the life and death cycles of stars. Part 7: Big Bang Nucleosynthesis, the First Minute. On December 5, 2022, at the National Ignition Facility at Lawrence Livermore National Laboratory in California, humanity achieved something remarkable. Scientists at the lab focused 192 lasers onto the inside of a centimeter-long gold cylinder, containing a single peppercorn-sized fuel pellet, containing 2 isotopes of hydrogen, deuterium, and tritium. The reaction produced more energy than was put into it. For the first time, we had harnessed the power of the stars. And yet, this is a process that has been going on naturally, in the heart of every star in the universe, for billions of years. Not only that, but the physics of the universe had worked out this nucleosynthesis in its very first minute. As the average temperature of the universe dropped to around 10 trillion degrees Celsius, around 1/1,000,000th of a second after the Big Bang, it was finally cool enough for quarks to bind into protons and neutrons, creating the building blocks for all the elements that would come later. But there was a 100 million year time gap before we saw the first stars begin to shine. So, when and how did those nuclei come together? In 1948, brilliant American doctoral student Ralph Alpher, working alongside his supervisor George Gamow, proposed a mechanism that would come to be known as Big Bang nucleosynthesis. It was a bold and inspired theory, but the brilliance of Alpher's work was somewhat overshadowed. The alpha-beta-gamma paper became the authoritative text on prestellar nucleosynthesis, and to this day provides the foundation for understanding how the high temperatures at the dawn of the universe could have turned hydrogen into helium via deuterium intermediaries. Around 10 seconds after the Big Bang, it was cool enough for some deuterium nuclei with 1 proton and 1 neutron to form. But in this hot cosmic soup, the temperature and particle energy were still so high that the deuterium nuclei were unstable. This is known by physicists as the deuterium bottleneck, and until it was overcome, nucleosynthesis simply could not progress. It was only after around another 300 seconds that the temperature dropped enough for deuterium to become more stable, and for additional elements to form. First, deuterium, with its 1 proton and 1 neutron, was able to fuse with individual protons. The result was, for the first time, a completely new stable element, helium-3. From this point on, the next cosmic creation was the more common type of helium, helium-4, consisting of 2 protons and 2 neutrons. Calculations based on the initial balance of protons and neutrons, and the energy available at this time, predicted that this would result in a universe that was around 25% helium by mass. And this is indeed what we find. Even 13.8 billion years after this energetic burst of helium creation, the universe is still around 23% helium. This observation alone is a stunning confirmation of Alpher's theory. And here we see another example of the fortuitous fine-tuning of the universe's initial conditions. Finally, after around 1,200 seconds of intense cosmic nucleosynthesis, equivalent to 20 minutes of the universe's existence, the nuclear furnace finally shut down. At this point, only 4 elements existed: hydrogen, helium, lithium, and beryllium. And with these basic ingredients, the stage was well and truly set for the formation of everything else. Even the deuterium and tritium that scientists fused in California in 2022 were themselves first formed in the heat of a newborn universe 13.8 billion years ago. This balance, 25% helium, 75% hydrogen, was, again, a fine-tuning. If nucleosynthesis had been slightly more efficient, it would have consumed all the hydrogen, leaving no fuel for later generations of stars. If it had been less efficient, the first stars wouldn't have been heavy enough to forge the heavier elements needed for rocky planets and life. The universe made just enough and no more. Part 8. The first molecule, the first 100,000 years. Life in the universe is a miracle of chemistry. And as far as we know, that chemical miracle has only arisen in one place. But where did those molecules come from? Some imagine that the warm and vigorous chemical environment on the newly formed Earth provided the perfect conditions to assemble organic molecules from scratch. But there's another theory, that the ingredients for life were not made on Earth, but among the stars in the depths of space. And indeed, we are finding compelling evidence for the stuff of life far out in the cosmos. Scientists have now identified over 250 complex organic molecules inside interstellar clouds and in the shells of material surrounding stars. The amazing truth about the universe is this. Without any special prompting or encouragement, the universe itself is capable of building molecules and performing remarkable acts of chemistry. And this space chemistry has its origins in the infant universe, less than 100,000 years after time began. The intense act of element creation during Big Bang nucleosynthesis had ground to a halt after just 20 minutes of the universe's existence. The ambient energy was no longer high enough to power nuclear fusion, but conditions were still harsh. The entire universe was still denser than the air we breathe, and the temperature was still too high for the lightweight electrons to slow down enough to be captured by the newly formed elemental nuclei. And yet, something was happening in the chaos. First created in laboratories in 1925, helium hydride is an unstable ion of helium bonded with hydrogen. In 1978, astrochemist John H. Black at the University of Minnesota proposed that it might be found in large quantities in space, specifically in planetary nebulae. The conditions inside this distant nebula are very similar to those that would have been prevalent throughout the universe for its first few tens of thousands of years. Even if this helium hydride is not primordial in origin, proving its formation in such an environment tells us much about its potential in the early universe. Big Bang nucleosynthesis was highly effective at creating atomic nuclei, but for the next 100,000 years, cosmic energies were still too high. As the ambient temperature dropped to around 4,000 Kelvin, however, these wandering nuclei were able to combine in a specific order. It is for this reason that helium today is considered the noblest of all the noble gases. It is the most inert and least likely to react because it takes an enormous amount of energy to strip away one of its electrons. But in the early universe, when all that existed were ions, this supreme holding power meant that helium was the first element to attract electrons and keep them, forming the very first uncharged atoms. This stability of helium, however, was sadly to be short-lived. It was still too hot for lone protons to capture electrons to make hydrogen atoms. So, the protons looked to helium and its balanced electrons, seeking an arrangement where they could share. Eventually, under the weight of these clinging protons, helium relented, forming the very first chemical bonds, and the very first molecule in the universe, creating the highly unstable helium hydride ions in the process. And yet, these short-lived molecules paved the way for the creation of other molecules, and the beginning of space chemistry. Around 100,000 years had now passed since the Big Bang. Here was another fine-tuning. The existence of helium, an almost inert element, became the necessary catalyst to kickstart chemistry in the cosmos. If the laws of physics had been just slightly different, if helium's ionization potential were lower, then protons and electrons might never have found a matchmaker to bring them together. Chemistry might never have begun. Part 9. The first atoms, the first light, the first 380,000 years. You might think you have a good understanding of the world around you. But this is simply not true. There is much, much more to reality than meets the eye, the ear, or the fingertip. In its entirety, for all our apparent perceptiveness, we are unaware of at least 99% of what's going on in the universe. For the first few 100,000 years of the universe's existence, it was entirely opaque, despite being filled with light. Such a concept is hard for us to imagine today, but since 1/1,000,000th of a second after the Big Bang, the photons that carried the majority of the energy in the universe were trapped in a maze of their own making. Nothing would change until the final formation of atoms. Eventually, it took 380,000 years of cosmic expansion for temperatures to drop enough, down to around 3000 Kelvin, for electrons to finally join the fold and create the first stable atoms. And when they did, the entire universe transformed. Electromagnetic attraction pulled electrons into stable orbits around atomic nuclei. Where they had once roamed free in the universe, electrons were now tightly bound to their positively charged partners, opening up empty space for the first time since matter was created. The photons that had been trapped in a maze for hundreds of thousands of years suddenly found their paths cleared. They could escape, traveling in straight lines without immediately hitting another particle. They were the first light to truly travel through the universe. What was once opaque was now transparent, what was once plasma was now gas, and what was once fragmented was now whole. For the first time in the entire history of the universe, we finally have a chance to see what was going on. In the 1960s, researchers Arno Penzias and Robert Wilson stumbled upon a faint but persistent radio hiss. They had eliminated all possible sources of interference, even the pigeon droppings in their antenna. The hiss remained, coming from every direction in the sky. They had accidentally discovered the cosmic microwave background, CMB, the afterglow of the universe's primordial fireball, now redshifted into microwaves by the expansion of space. The detection of this redshifted fireball glow, now stretched out to just 2.7 degrees above absolute zero, was the conclusive evidence that the universe had indeed begun in a hot, dense state. Even though it dates from a time some 380,000 years after the moment of creation, it is vindication for all the theories of how things had unfolded in the intervening period. Because, while Penzias and Wilson saw a remarkably consistent microwave hum across the night sky, later instruments designed to study the CMB detected very slight variations, places where it was a tiny bit hotter or colder by a few hundred thousandths of a degree. Those density variations provided the seeds for the large-scale structure of today, because they contained more matter, attracted more matter, became denser, and pulled in yet more. Those variations appear to be largely random, as would be expected, the result of subatomic quantum fluctuations inflated to grand scales via inflation in the first fraction of a second after the Big Bang. But closer analysis also reveals another strange pattern hidden within the CMB, a pattern that is also mirrored in the large-scale structure of the universe today. Before atoms formed, when the universe was still filled with an opaque plasma, it was dense enough for sound waves to travel through. These waves originated from the conflicting forces of attraction and repulsion in the energetic, seething soup. In a sense, these compression waves through the matter of the early universe were sound waves, and are consequently known to cosmologists as baryon acoustic oscillations. And yet, this phenomenon did not survive atomic recombination. As the universe reached the critical temperature of 3000 Kelvin, allowing electrons to be captured and atoms to form, the expanding ripples suddenly stopped in their tracks. The baryon acoustic oscillations were all frozen in place. Now, some 13.5 billion years later, the universe has expanded, but the pattern left by these frozen ripples can still be discerned in the overall structure of galaxy clusters and superclusters. The imprint of the universe's first light may have been stretched and faded into a shadow of its former self, but it will be trillions of years before it disappears entirely from our view, giving cosmologists of the future plenty of time to decode its mysteries. And as we do, we are confronted with the staggering truth. The universe doesn't just exist. It is inscribed with the laws that permit existence. The fine-tuning didn't stop with the fundamental constants. It extended to the initial conditions, the balance of matter, and even the distribution of energy. Every discovery, from the Lyman alpha forest to the cosmic microwave background, reinforces the same unsettling conclusion. We live in a universe that appears exquisitely designed to produce stars, galaxies, and eventually, observers who can marvel at it all. The ultimate question is not how the universe began, but why it began this way. Why are the laws the way they are? Why was symmetry broken so perfectly? Was this a grand cosmic fluke, one success among countless failed universes? Or are we seeing evidence of a deeper principle, a kind of meta-law that governs the creation of universes, ensuring that at least some of them will be capable of hosting life? Science may never answer these questions. They may lie beyond the reach of the experimental method. But as we look up at the night sky, armed with the knowledge of the cosmic lottery that allowed our existence, we cannot help but feel a sense of something beyond mere randomness. A sense that the story of the universe is not just a story of physics, but a story of potential, of complexity arising from simplicity, and of a reality that seems to have known, from the very first moment, that one day it would be observed.